This is Physics 2212 Lab 4, Circuits and Capacitors. So a little introduction. Purpose of this lab is to predict the behavior of circuits with different components and then examine their behavior using the PHYS circuit construction kit and then measure experimental current and potential differences and compare calculated and experimental values. And then our results preview. The current in the 2 resistor circuit was 0.02 amps. The experimental and calculated values matched. And then in an RC circuit, as resistance increases, the capacitor charge and discharge time also increases. And then for the experiment with an RC circuit, our time constant was 5.988 seconds. So some important things to know here. Our node rule, it's kind of blurry, but the current entering a junction is equal to the current leaving that junction. Yeah, and then for the loop rule, just the difference in potential for a round trip path is 0. So pretty simple stuff. The resistance of a component is just change in voltage divided by the current. And then for resistors in series, equivalent resistance is just the sum of each individual resistance. And then for ones in parallel, 1 divided by equivalent resistance is equal to the sum of 1 over each individual resistor. And so for capacitance, just measures how much charge can be stored in a capacitor. So we have our charge divided by change in voltage, or just the size of area of a plate times epsilon naught over the distance between the plates. So our visual model here is our 2 resistor circuit. Here is our RC circuit. And then for part 3, when we measured change in voltages across different components, that's our model here. So our system includes the ammeter/voltmeter depending on what we're doing, and then our surrounding includes the circuit and thus the induced current and potential difference. So part 1, our 2 resistor circuit, as you see here, we got our 2 resistors in series and our ammeters. The predicted current was 0.0204 amperes. Actual current was approximately the same, 0.02 amperes, as seen here. If we reversed an ammeter, the current would just be going the opposite direction through the ammeter, so it would read negative. Part 2, our open circuit here, we know the current is 0 because it's an open circuit. And then our predicted value for potential difference is 3 volts because each of these batteries is 1.5 volts. So add them together, you get 3 volts. And that's what the actual experimental value was. Part 3, where we measure the potential differences around each circuit component. You can see here in the graph how the batteries increase the voltage and then the voltage drops as we pass through both resistors. And this kind of like assumes that the wires and ammeters have approximately 0 resistance. So part 4, our ammeter in parallel. Again, this decreases the resistance because this is a parallel, as we saw when we calculated equivalent resistance in parallel. So the current increases from 0.02 amperes to 0.06 amperes. So overall current increases. So calculating resistance of the resistors, our 47 ohm resistor was approximately 48 ohms, 100 ohm resistor approximately 102, and then our ammeter wire were assumed to be negligible, so 0 ohms. Our RC circuit here, we have our resistor/light bulb type thing, and then we have our capacitor here, and it's charging as the current flows through it. So we see that from our results that as resistance increases, our charge and discharge time increases as well because it takes longer for the charges to move and thus longer time for the capacitor to charge and discharge. And so as we were discharging a capacitor, we measured the time-dependent voltage at each second to see how it relates so we could find the time constant, and we plotted the natural log of the voltage divided by 9 volts, which was the initial. And then we did some algebra here, taking the slope of our plot, and found that the time constant of our circuit here with 30 ohms of resistance is approximately 5.988 seconds. So we saw that our calculated resistance values were greater than the actual resistance values in the simulation. And this is basically just because the ammeter was not precise. It only showed to the hundredths place, and there's really no room for like any other error because it was entirely simulated. And so our sources of error, we saw our ammeter precision and then rounding during calculations, and also assuming that resistance in ammeters and wires are negligible because this was an idealized simulation and not real life. And so as we see here, if we use an actual ammeter instead of like the ideal simulated one, the actual one has non-zero resistance, and so current would slightly be decreased and the readings would slightly decrease. And then if we charged a real capacitor with no resistor using a real battery, the ideal model would predict that the capacitor would reach full charge nearly instantaneously, but this is not true in real life because we know that wires have non-zero resistance no matter how small it is, so it would slightly increase the time for the capacitor to fully charge. And also capacitor resistance would have to be considered as well when finding the charge time.